Hello, everyone. This is Ganghua from Warmpex AI Research. Today, I'm going to talk about how computer vision and AI technology can help boost brick and mortar convenience store retail operation. A little information about Warmpex AI Research. We are the research branch of Bianlifeng, a newly established and fast-growing convenience store chain in China. To date, we not only own thousands of stores, but also our own manufacture and warehouses. Just to give you a sense how our business is growing, in 2017, marking the first year our stores are in operation, we opened up a total number of 200 stores. In 2018, we added another 600 stores. In 2019, we added another 1,000 stores. Despite the pandemics in the past 2 years, our stores have been continually growing. For example, our year-end goal this year is to add another 2,500 stores. With our business growing like this, there is an urgent request for us to digitize the full operation decision of our operation process. The reason is simple. If we don't do this, we simply cannot recruit and get sufficient number of qualified storefront managers to run our stores if we keep relying on human decisions. Indeed, if we have a retrospective view of the past 15 years, the internet has been powering a lot of economic growth. One of the major reasons is that the internet naturally forms a digital world. This makes algorithmic-driven digital decision to be super convenient, and the subsequent digital operations would feed more data back into this digital world. But if we look back into convenience store business, the story is totally different. In order to achieve full digital decision, the first step indeed is for us to digitize the information resides in this physical world in our storefronts. Then we may leverage algorithmic-driven digital decision and factor those decisions back to physical operations. This roughly corresponds to the perception, cognition, and manipulation parts of an AI system. We believe that computer vision will play a key role in the digitization process, and subsequent digital decision will mainly made by machine learning and operations research. As we have mentioned, the whole operation loop in our design has 3 components similar to what we have in the AI system. So we can actually view this full operation loop as a robotic system, and indeed a core robotic system, because humans are involved in this process, especially in the execution part. Next, I'm going to use a case study to show how we fulfilled this full loop of digitization, decision, and execution. So the rest of my talk will be organized into 3 parts. In the first part, we're going to talk about how we're creating a digital twin of our storefront using computer vision technologies. Then we're going to use a case study on assortment planning and shelf space allocation to feed the digital information into this decision process to drive revenue growth in our storefronts. Last but not least, we're going to talk about how we're using this digitized information to ensure the offline execution is done as we expected it to be. The first step of our digitization process is to have a 360-degree cameras mounted in robots to scan every single corner of our storefront, as shown in this video. Once we captured the full storefronts using the 360-degree camera, we can then leverage structure from motion technology to reconstruct the 3D of the storefronts. The slides show the point clouds reconstructed from the structure from motion algorithms. At the same time, we also run a deep learning-based 6DOF pose detector to detect all the shelves in the 360 video and simultaneously identify their 3D orientation and position. With prior information about what types of shelves we have in store, we can then fully recover the digitized version of our shelf space. As shown in these slides, different colors show different shelves. Once we have digitized the shelf, we want to go one step further to create a digital twin for the products presented in the shelf. This is achieved by 3 product imaging cameras mounted in our robots. Because we have robots running in the store, we have a chance to actually identify the best spots for the robots to take those product shelf images. The left side and right side of the figure both shows the best position and view we identified for the robots to take the image for each shelf. And here, we have more visualizations about the surface of each shelf and its normal orientations. And here are some examples about the product shelf image we take from the robots. They are arranged in the up, middle, and low position because we have 3, as we mentioned, we have 3 cameras mounted in the side of the robots. Then once we have these images taken for the product shelf, we then can run category independent product detection algorithms to detect all the products presented in the shelves. This photo shows some examples for some product detection results in some regular shelves. Here are some more examples of the product we detected in our refrigerators. And here are some more examples. Once we have detected the products in the shelf, we can then run a product recognition algorithms. In order to keep the flexibility and scalability of our product recognition system, we take a retrieval-based approach where we index the example images of each product SKU into our database, and subsequent recognition was done by cropping the detected product image and query it against the database. Here are some recognition results we showed here, where we have a query image of a certain SKU and the top results returned from our database. And here is another example. What I want to mention is that although the query image is actually quite unclear about what exact product is there because we indexed the similar photos in our database. We actually successfully recognized what kind of product SKU is this, the photo presented. Once we fulfill these two steps, we can then recover the full product shelf map. And this slide shows two results from real photos taken from our store. For each example, the left side shows the real photos we are taking, and the right side shows the products we recognized from those photos. This looks so far so good. You may immediately come out with a question. How could this help increase sales revenue for our storefronts? So we need basically to hook this information into something more related to sales. So we're going to route this through an example of assortment planning and shelf space allocation. Before this, we're going to divert a little bit from computer vision and talk a little bit about something unique in brick and mortar stores when we compare it with online stores. The most prominent difference is indeed that space is the most precious resource in the physical store because we can only rent much space to when we are setting up a store. That means the display place in our shelf is limited. The physical limitation limited us to limited the number of SKUs we can present in our product in the shelf. We all know that if you don't present the product in the shelf, there's not going to be any sales happen. So assortment planning becomes a very important task actually in storefronts. Versus if we're looking to an online store, literally we can present unlimited number of SKUs because we simply need to add more web pages. But of course, we have a choice to rank different SKUs differently so that we can promote those products which could sell well. So in online store, we don't have assortment planning issue, but in physical stores, we do have issues to address on assortment planning. So the problem we need to address in this section is how can we most efficiently allocate spaces to different SKUs such that we can maximize our sales revenue. This is indeed addressed by a mathematical model for assortment planning and facing assignments. So before we establish our mathematical model, let's have a deeper understanding of what would happen if a customer comes to our store. There could be several situations happening. In the first scenario, the customer knows exactly what he or she wants to buy, and the product is also available, presented in our shelf. Then in this case, the customer would be happily buy the product and leave our store. In the second case, the customer knows exactly what he or she wants to buy, but the product is not available in our store. Either we didn't present it, which is called out of assortment, or we have sold out it, that's called out of stock. In either cases, the customer would usually present several behaviors. He or she would either buy a substitution or simply not buy anything and delay it to the next time he or she comes to our store, or we could permanently lose this sale. In the third situation, the customer does not actually know what to buy, but just wandering around our store to buy some random stuff or buy nothing. This understanding of customer behaviors actually comes out of our exogenous demand model. We regard the demand of each SKUI to come from three parts. The first parts are what we call the initial demand of item I, which is modeled by three parts in this equation. The DI mean we call the base demand of a product SKU. The KI is the facing number assigned to it. All of us know that in retail, it is well known that if we assign different facing numbers to a product in the shelf, it would actually result in different sales volume. And this effect is modeled by parameter beta I, which is called the space elasticity parameter. So the initial demand is DI min times KI to the beta I. The second and the third term in this equation actually models the out of assortment substitute behavior and the out of stock substitute rate. I won't get much more into details for this model, but just want to show you this equation here. And there's a bunch of parameters we need to estimate based on historical data to be able to calculate the exogenous demand. The parameter theta actually could be estimated by nonlinear least square given historically observed demands and facing numbers from sales data. Here, the computer vision algorithms we used in the first part to digitize the shelf and digitize the products actually serves as our information sources. Once we have estimated all the parameters of our exogenous demand model, we then can establish a mixed integer program to jointly optimize for the assortment and the facing assignment. In this equation, pi I is actually the selling price and profit of product SKUI. DI KI is our exogenous demand. Here, the capital KI is the cap of facings for each SKUI. Lowercase wi is the physical width of each SKUI, and capital WI is the cap of shelf width for each SKUI. We want to constrain that the facing assignment for all the products SKU would actually less than the total shelf width. We want also to note that we have a joint optimization problem here where if we assign KI to 0, that essentially means that the SQI is not selected in the assortment planning. So we achieve assortment planning and facing assignment in a single optimization problem. Once we can do this optimization, we actually can achieve our goal that we are going to have a unique planogram for each of our 1,000 stores. So indeed, that's what we do in our store operation. We not only using algorithms to select the product we want to sell in each store, we even create a planogram and give the planogram to the storefront managers so that they can present all the products according to the planogram. Now here comes out another question. Will the storefront managers do exactly what we asked them to do? Indeed, if you are in offline retail for sufficient long time, you will know that whenever we have operations in the physical world, like a quality control becomes an essential thing to achieve your goal. So in this section, I'm going to briefly talk about how we are ensuring the offline execution is done as we expected them to be. That's achieved through our redigitization process, where we are going to do post-check when products are on shelf, okay? So that means whenever we give the planogram to the storefront manager, they are required to display all the products as designated by the planogram. Then we're going to run the robots again to scan the storefront, the shelves after the storefront manager actually finished all the present all the products on the shelf, and we're going to compare the recognize the product display in shelf to the assigned planogram, and to see if there's a lot of difference or not. This slide we show one example here. As we can see, the middle of the image are the product shelf images taken from our robots, and the left side is the recognized product display in shelf, and the right side is the assigned planogram. We can actually compare row by row whether they are matched against each other. Obviously, here the top row is not matched against the assigned planogram. The same to the third row. And here is another example. As we can see, in the second row, we are actually missing some products because the products are not presented with sufficient facing there. Here are here is another example. So our business outcome is that by executing this flow loop in our in-store A/B testing, carried about 5 to 10% GMV increase on selected SKU categories. So I want to come back to make a comment about the role of computer vision in this case study. First, computer vision technology actually provided more accurate information about the actual product facings to drive the assortment and facing assignment model. And secondly, it ensures that the storefront managers to execute the planogram in the desired fashion. Because once we design the difference, we're going to send some work orders for them to fix those. So this actually ends the major part of my talk, but I want to spend another 1 or 2 minutes to simply show some other applications of computer vision in our storefronts. Indeed, we have some intelligent cameras where we can detect the customer coming in and out of our office, our storefronts, so that we can greet them and say goodbye to them. Here is another example. We call the intelligent reminder. In our store, in order to ensure our service quality, we have very strict operating SOPs in our store. In this case, if a customer eat lunch or dinner in our store and left some garbage in the tables, then our SOP actually required the storefront managers to clean them up in 5 minutes. So the storefront manager are really busy, so they cannot come to the dining areas very often. So we actually use a camera to computer vision to detect when a desk is dirty and actually send a working order and a reminder to the storefront managers so that they can clean these tables in a timely fashion. Here are some more examples where we can detect whether the dust bin is dirty or the some of the dust bins are presented in the right place or not. Of course, we're using computer vision also to try to detect theft in our stores. Here is another example where we actually are using some robots to help uh, the sales activities in our stores, where the robots actually would automatically cover the lunch boxes. So broader role of computer vision in brick and mortar retail includes capture more accurate information about the status of the store, ensure the quality and service consistency of the storefront operations, and anti-theft. This would end my talk. Thank you very much. I would be happy to answer any questions.